can write, however, J left as J of A minus J of B, where J of A would be h bar k over m a squared, and J of B would be h bar k over m b squared. You see, the current that exists to the left of the barrier has two components, and it's very intuitive. It's the current that would have been brought alone by the incoming A wave minus the current that would have existed alone from the reflected B wave. B is the reflected wave. So that's very nice. There's no interference between these two terms. We can really think of a current that is associated to the incoming wave and a current associated with the reflected wave. So this suggests how you should define a reflection coefficient. Reflection coefficient R would give me the amount of current I get reflected compared to the amount of current that there is incident. You see, the incident current is going to be partially reflected and partially transmitted. So an idea of a reflection is the value of the reflected current divided by the incident current. It's a definition, but it's a reasonable definition. And then if it is this ratio, because of these expressions, it happens to be B over A squared. And that's an interesting number. Now there's some physics in it. It tells me how much of the probability gets reflected as a function of the probability that is incident. So that's a good measure. If you get a reflection coefficient of 1/10, then you would expect 1/10 of the particles to be reflected. Now, we don't have particles yet. This is a non-normalizable solution, but still, this will be the intuition very soon. Now, we could have a transmission coefficient as well. And here is something that we sometimes make a mistake. T is going to be the transmission coefficient. And how should we define it? There is a temptation to define it, well, the coefficient B over A gives me this, then maybe should it be C over A? But actually, while C over A gives you some idea of how big is the wave to the right compared to the wave to the left, that's not what we should call a reflection coefficient. And the reason is that I will call this current JC, and that's the amount of probability, because it's a current associated to the wave C, and that's the amount of probability that is being carried by the transmitted wave. That is the probability, not necessarily C over A. So the transmission coefficient will be defined to be JC divided by JA. And then JC divided by JA, JC has an H bar K bar, and JA has a K. So this is not equal to this ratio, but it's actually K bar over K, C over A. So it's not just this number. The reflection and transmission coefficients really originate from probabilities, and the probabilities for these currents. And therefore, there's no, it would have been very hand-wavy and actually wrong to think it's C over A. And these definitions, because after all, this is a definition, make some nice sense, because you have JL, we said is equal to J right, but JL is JA minus JB is equal to JC, and therefore R plus T, the reflection coefficient plus the transmission coefficient, which is JB over A over JA plus JC over JA is equal to JB plus JC over JA. And you see here that JA plus JC is indeed equal to JB. A minus, I'm sorry, I got this wrong. Yes, where's the eraser? I should have passed the B to the other side. This, of course, implies JA equals JB plus JC. And this ratio is equal to 1, which is something you usually want when you define reflection and transmission coefficients. They should add up to 1. So now we got an idea. Yes, with this solution, I can understand the reflection and transmission coefficients, but do these apply to particles? Well, the good news is that it roughly apply to particles, as we will see with the wave packet soon. If you send a wave packet, it's going to have some uncertainty in momentum, it's going to have some uncertainty in energy, but for some energy, suppose the wave packet doesn't have that much uncertainty, basically the probability that the wave packet bounces, it is the reflection at that energy that is the main energy that the wave packet sends. If your wave packet is very broad over energies, well, then it's a more complicated thing. But as long as the wave packet is such that it basically has one narrow band of energies, the reflection coefficient associated to this calculation is the reflection coefficient or reflection probability for the wave packet that you're sending in.